Right, so for the next topic, we call it heuristics. And why we call it heuristics is because we want to talk about uh, strategies to solve a problem that actually try to mimic the way that human solves a problem. Because it turns out that sometimes when we run into some problems, it's actually not easy to get a solution. Now, this is an example of the problem. This is called traveling salesman. We're going to go into what exactly is this problem, but the key point here is that we are using this as an example of a problem that we call computationally demanding. So which means that there is a certain class of problems that are too hard to solve. It means that if you actually want to solve it for real, the current computational power that we have will not be able to run the algorithms to completion. There are different ways to solve such a problem, and we are going to take a look at a couple of them in this topic. Now, the traveling salesman problem is essentially a problem where you need to make a round-trip tour of a number of places. Now, for example, right, so if you think about, let's say every day, if you work for a logistic company like DHL, FedEx, or the Singapore Post, so they have a number of packages that they need to send to the recipients. So in the morning, they will go from the headquarters or the warehouse, wherever it is. Then they have a list of addresses they need to go to. And at the end of the day, they have to come back to the warehouse again. Now, the sequence in which they go to different places is going to determine how efficient the whole trip is going to be. Because they may, if the warehouse is somewhere in Changi, they may go in a particular certain route around the island instead of going zigzagging here and there in order to minimize some criteria. Now, this is another example, right? So every Olympic, we have the torch relay. So the idea is to make a certain route where there are different runners, and the different runners are going to pass the torch to one another. Now, these are going to involve a lot of different places. So in the most recent case, which is Winter Olympics, in this case, they want to visit 80 localities. 80 localities meaning that there are going to be 80 factorial different permutations in which we can visit the different places. So that is going to result in a lot of permutations, and this number of permutations is going to be impossible to actually do it with the current computers. It means if you're going to do this in a brute force way, trying every single possible permutation, we will never end, right? So in case, even if you have a computer that is very fast, it will take a lot of time to do it. Now, this is a simpler instantiation of the problem, but the idea is that, let's say, this is the map of Ireland, and there are cities in Ireland. So in this case, let's say, Belfast, Cork, Dublin, Galway, Limerick, and these 5 cities have distances. And normally, this is the way that we formulate the traveling salesman problem. You're given a distance matrix. Now here, the distance matrix, you're only given half. And you're given half because the distances are assumed to be symmetric. So if you know how to go from one city to the other, then the other way around would just be exactly the same distance. So for example, Cork and Belfast, right? You go from Cork to Belfast is 4 to 5. For you to return from Belfast to Cork is going to be the same. Now, you want to visit all the cities, and you want to visit them exactly once, and at the end, you're going to return back to the original starting point. Now, that is the problem. It's simply stated, but it's actually very difficult to solve because the minimization that we are trying to do is going to involve too many possibilities. Now, if there are a small number of cities, you can still do it, right? Let's say if you give you a map of the cities, you probably can design a route that is reasonable, and your method of doing it probably is to look at the cities and try to go and find a nice route. And this is one example. So generally speaking, if it looks like this, you tend to minimize the distance because there isn't a lot of crossing. And the crossings generally represent a wasted distance. So this is part of what we call heuristic. Heuristic in the sense that sometimes there is a certain strategy that a human would use to solve a problem, and we are using that strategy to try to design an algorithm that would give us a good enough solution. Now, this is the Turing-Salesman problem, and it's up to now, it's still not solved yet. Not solved in the sense that we cannot yet have an algorithm that will solve the general case and still be able to run in good time. There are a lot of approximations, and there are a lot of ways to try to optimize the runtime. So in this case, here is the map of the US, right? So this is just an example of, there was an effort to see whether or not we can actually devise a route that will go all over the US, visiting every place exactly once. Now, there are 13,500 localities, so it's impossible to actually compute it for real, but there are a lot of constraints and tricks that you can do to optimize the computation. So for example, if you know that certain areas don't have any much of the cities, right? So there could be mountainous areas and so on, so you may do certain kind of processing, but in the end they could solve it in 5 years. But even so, this may not be generalized, because you can solve it in one particular case using a lot of information that you know about the land and how the layout is given. But in the general case, you want to be able to solve problems without making a lot of assumptions. Why? Because there are actually a lot of applications. Although we talk about Turing-Salesman in terms of traveling, geographically, but in reality, actually there are a lot of applications to Turing-Salesman that may not even involve geography. Now, this is an example, right? Now, something like this is like a printed circuit board, and the idea is that a lot of the electronic devices that we have, whether it's a computer, whether it's your laptop, or things that actually have some computational components, they will have this kind of a motherboard where a lot of the electrical components are actually there. Now, there are a lot of chips there inside this printed motherboard, and you can even think of this thing essentially like a small little city, because there is like a power supply, there's like a battery, right? But in this case, it could be a battery or some power supply that comes from a certain place, and they need to deliver power to certain places, and there's going to be a certain connections that you need to make between the different parts, because it's a circuit, so the electrons are going to be flowing. Now, one of the problems that they face here is to optimize for the layout of the board. And the layout of the board meaning where you place certain chips, because there's certain kind of connections that you need to make. And the placement itself is important, because if you place them strategically, in theory you can save a lot of materials. So if you cut down the space or to cut down the distances, you minimize the use of the metals that you need to actually build one circuit board. And of course, for one circuit board, it doesn't really matter, but the reality is that when you manufacture this, you manufacture this in the thousands or even in the millions. And in that case, a lot of the cost savings are actually important. Okay, so of course there are also transportation and logistic problems, and manufacturing and so on. And in this case, a lot of cases, the number of cities can be 1,000 or more. So this is what we meant by saying that a lot of problems that we face in computational thinking, they can be abstracted, and once you can abstract them, you can apply it to many different scenarios. Now, one of the things that we try to do is to quantify how many possible tours do we need to do to actually get a meaningful solution. Now, if the objective is to get the optimal, and here we need to define what is the criterion for optimal. Optimal could mean the lowest distance, which is the most common, but in some cases you might want to aim for something else. It could be the lowest cost or the lowest time, but all it involves is just a matter of how you represent the edges. Now, once you have the distance matrix, then it's a matter of computing each tour, and we can do this exhaustively, meaning brute force, by generating all the possibilities. So if you do this for 5 cities, it's going to be 12 possibilities. 6 cities is 60, 7 is 360, and so on. And you see the number is actually growing very, very fast. And by the time you get to 25 cities, in fact, we have too many zeros that we can't actually compute it in real time. Now, the number of tours that is going to be involved is n minus 1 factorial divided by 2. Now, why is it n minus 1 factorial divided by 2? Well, firstly, we are trying to generate tours. So let's take a look at what kind of tours they are, right? So for example, so in this case, let's say you might have A, B, C, D, E. So this is one tour, in which case you go from A to B, B to C, C to D, D to E, and then E to A, right? It's a round trip tour. Now you could also go on a different tour where you go from B to C, to D, to E, to A, and then return back to B. Now if you look at all the possible permutations, it's going to be 5 factorial. But because this is essentially a circle, so once we discover a particular permutation, if we shift everything by 1, for example, A goes to the other end, and we start the tour from B, it turns out that all the distances that we get are still the same. Because BC here still exists here, the CD here still exists here, DE, EA, and AB, right? So effectively they involve the same set of distances, which means that any shift, any circular shift through the permutation is not going to change the total distance that is involved. So which means that I can divide this by 5 because in fact I don't need to look at all the possible permutations. I just need to look at the ones that are not duplicates, because for every permutation there are 5 duplicates that will give me exactly the same distance, so I wouldn't bother with this. Now, so this will give us 5 factorial divided by 5. Now the other point that is also important is the distance. Now, so it requires some assumption as to whether the distance is symmetric or not. So if you go from A to B, would that be the same distance as going from B to A? Now in some cases the answer is yes, because if it is a straight distance, you go from A to B, B to A, they are the same. Now in some of the problem, the answer is no, because depending on the directions, right? So for example, some roads is a one-way street, so you can't go back the same way. So which means to go one way and to return back might actually involve a detour. So if the distance is symmetric, meaning that it's the same going either way, then we can divide it by 2, because I can reverse the flow of the permutation and I will get exactly the same distance. For example, instead of A, B, C, D, E, I might have a tour that is A, D, C, B, A. Now in this case, the distances, it goes from A to B, in this case is B to A, so B to C, here is C to B, everything is reversed. But if everything is the same, then essentially they are still the same distance. So which means we can divide it by 2. Now of course if the distance is asymmetric, that means it's not symmetric, you don't divide by 2. So then the total number of possibilities that we need to take into account if we want to get the optimal answer is n factorial divided by n by 2, which is the same as n minus 1 factorial divided by 2. Okay, now minus 1 comes because of the circular permutation, because you have to come back to the original point. If you don't have to come back, then you don't need minus 1. You need minus 1 because it's a circle. Now the divide by 2 is because of the assumption that the distance is symmetric. If the distance is not symmetric, then you don't divide by 2. Alright? Now what it simply means is that you might have an algorithm that discover a tour, and the tour will be a round trip tour. Once you discover a tour, you might make certain assumptions about where the tour starts from. But because it's a circle, effectively you can start from any point. So let's say you design an algorithm that will give you A, B, C, D, E. And now it doesn't actually mean that you have to start from A. It just means that it has given you now a circular tour, to the extent that you can choose where your starting point will be, and anywhere you start, in any direction, will still give you the same distance. So the algorithm that you have is just going to design a tour as to where you actually start from, that is not important. All right? Now, any questions so far about this? Okay. Now, we are going to talk now about what is a computationally intractable problem. Oh, by the way, there are some codes inside last week's graph lab, the Python lab that we gave you, that would actually implement some of the logic that we talked about in class today. Now, there are different strategies for solving traveling salesman problem, and these are the so-called initial strategies. Like, if you don't know any better, then we will do one of these, right? So, okay, one way to do this is eyeballing. So what we mean is that if the problem is defined in terms of like a geography, geospatial thing, and you only face a single instance of the problem, you put it on the map, you can see it, you can probably figure out what is going to be the best route. But of course, you know, that is not going to scale because you can't eyeball everything, and there is a certain limit to how many you can handle. Now, another possibility is exhaustive search, which in other words is brute force. So brute force is not going to work if there are too many cities, because the complexity is O(n) factorial, and this is actually very, very complex. The third one is random search. Random simply means that you're going to randomly generate solutions, and then you see among the solutions that you generate randomly which one is the best. It is a valid strategy, except that it's a strategy that doesn't give you any guarantee, because you may be unlucky and you may randomly be generating all the bad solutions, so you don't actually get a good solution. Now, instead, what we're going to do is to approach this as an optimization problem. Now, what does it mean to have an optimization problem? The keyword is optimization, right? So you want to optimize something. So what is it that you want to optimize? Now, most of the time, we are going to talk about a single objective function. In more complex problems, you might have more than one objective. But in the case of traveling salesman, for example, the objective is simple. You want to minimize the distance. There is no other criteria, only the distance. And this is so-called objective function. And we want to minimize this. We can seek solutions that will give us a smaller value in terms of the distance. Now, if we get the optimal solution, then the very, very best one is called the optimal solution. Okay, so as an example, traveling salesman is the distance, and the goal is to find a route with as short a distance as possible. Now, there are a lot of examples of optimization problems. In fact, some of the problems that you come across in the past, things like the lab test, question 4, that is an optimization problem because you are supposed to minimize the number of vertices that you need to cover all the users, right? So any kind of problem where the solution depends on maximizing or minimizing some objective function that is well defined is an optimization problem. Now, if you want to have an ideal algorithm for optimization problems, in general, you want these 3 criteria. First criteria is that it's going to be fast, because you don't want to wait very long for a solution. And here, for practicality, we are going to define fast in terms of whether or not it can run in polynomial time. So polynomial is n, n squared, n cubed, and so on, right? So if it runs above polynomial, meaning once you get to, for example, exponential, like 2 to the power of n, or factorial, like n factorial, then it's not going to run fast. Now, the second case is general. So what you want is for this to work well on all instances of a problem. That means that your problem, you don't have to make any assumption about how the problem is specified. You can still find a solution. So the final one is optimal. Optimal meaning that it's going to find the exact optimal solution. It's not going to find anything worse than that. It's going to find the very best one. Now, this is the ideal, right? But we don't live in an ideal world. And generally speaking, if you want fast, cheap, and good, right? So you can pick 2. You can't get all 3. Because, you know, there are some trade-offs that you make in order to get a particular property. So you want to have something that is good and cheap, it won't be fast, right? If you want good and fast, it won't be cheap. If you want fast and cheap, it won't be good. So you have to pick 2 out of 3. Now earlier, we defined 3 criteria. So in a way, it's the same case here. We want to find a solution that is fast, general, optimal, but we can't get all 3. So you're going to pick 2. Now what does it mean to pick 2? Now, depends on what is the trade-off that you are willing to make. Now, if you want to have a problem, a solution that is both general and optimal, meaning that it's going to cover all cases and it's always going to get you the best solution, then the only way that is available to you is brute force for this kind of problems. That is what we call computationally demanding problem. But it's not going to work well because it's going to be extremely slow. You may not even get a solution at all. Now, you might be able to, in some cases, to get a fast and optimal solution, but you may not be able to apply it in general. Now, for example, if you're told beforehand that, let's say, that all the cities are lined up along a straight line, then you don't have to try all possible permutations. For this special case, there is a way to solve it, which is just follow the line. And in that case, it's going to be fast, it's going to be optimal, but it doesn't cover all the possible cases. So most of the time, the trade-off that we consider to be acceptable is to do it fast and in a general way. That means that I don't need to make any assumption about my problem, and I can solve the problem fast. Now, which means that the trade-off that I'm taking is to sacrifice the optimality. So can we find a solution that is good enough? Good enough here means that you may not get the very best, but you're going to get somewhere close enough that for all practical purposes, it will still fulfill your objective. So for example, right, so you work for FedEx and they ask you to design a route in the morning. If you're going to take 5 years to do that, your boss will say, no, what's the point, right? Because you have to do it for that day. Now, you might be able to get a second best solution or some approximation in a few minutes. And in most cases, that solution is going to be good enough. You don't actually need to optimize to the last drop of gas, right? Or to the last second of the traffic, because anyway, there are a lot of other factors that are going to come in. So the way that we devise solutions that are fast in general, it turns out that a lot of times is to use heuristics. Heuristics means like some strategies that are actually intuitive for us to actually employ. Now, what are some examples of such heuristic strategies? We're going to cover 2 in class. They are not the only 2 that are available to you. I think at the end of the lesson today, I'm going to outline some other solutions. But for now, we are going to talk about 2. One is called greedy, right? Because it's the way that humans solve the problem is by being greedy. The other one is what we call local search. Local search meaning that most of the time, we don't start from first principles. What we do is to take an existing solution and then try to improve it, right? So, for example, let's say if you work for FedEx, they give you a route, then they will say, show me yesterday's route, and then I'll just make some changes to it so that actually I can get something that is good enough. Now, both of these, or in fact most of the heuristic techniques, cannot get you the optimal. Because remember, the whole point is we are sacrificing optimality in order to gain speed and generality. So, which means that we cannot guarantee that you're going to get an optimal solution. It doesn't mean that you will not. Maybe by chance you get optimal, but it will not guarantee you that you're going to get an optimal solution. Now, but if you're interested in the theory of it, there are a lot of efforts that are being put in order to prove some level of performance bound. So what this is usually expressed is in terms of a factor of the optimal solution. So for example, someone might say, all right, so if you follow this particular algorithm to solve the traveling salesman problem, you will not get the optimal solution, but we can guarantee that you're going to get within 63% of the optimal value. So usually it's expressed in terms of that. And we are not going to go into this within the course because we focus on the application. But in some textbooks, you'll be able to find a proof. If you're interested, you can see, but the proof is tied to the algorithm. That means that it's not proven for the problem, is proven for a specific algorithm that tries to solve a particular problem. Okay? So we're going to introduce 3 algorithms. So 2 greedy algorithms and 1 local search algorithms to solve Turing-Salesman problem.